Mason said just no, we're not doing it. So,
Can you do it?
I could.
So how are you gonna do it?
I'm gonna wait.
So
It's gonna be like 15 minutes.
okay.
Design programming was Mason. Robotics acts.
What's about
to like go in a straight line, so it wouldn't like not work. And so we thought that was pretty smart. So.
Denarius, the mechanical design?
Our original objective was to do the crater crossing. We used 9 mechanical parts for less errors. But we then expanded onto more challenges.
Mason, programming.
So for the programming, me and McKay used different ways to program it. Like I used rotations for it to turn and move, and McKay used degrees
And
to
then
make it move. And so
And the more time that continued, the more people that came in and started working on it. Also, the same type of patience degrees.
Okay.
Kevin, some of the robotic facts.
So our robot was originally used for crater crossing. That's what we used it because we got here.
Oh, you got here. Oh, okay.
This is your okay, your programming.
So how many different robots did y'all go through? 5. Okay.
And this was our first time at state, and we chose this. And
Okay.
the other robot.
And why did you choose tracks over wheels or tires?
Because normal wheels can't get over this with that much precision. So, and we have tested these, and these have a little more precision going over crater crossing. So,
And we created 2 copies of the robot, and we put together 2 different teams, and we edited it all for for what we needed to, and we did a mini competition to decide which robot would be competing.
Okay.
And this robot won.
Gotcha.
And later on, we discovered that this, when it moves, it bounces a lot.
Mhm.
But when we add more of these,
Right.
it bounces a lot more, but it affects it less. So,
Okay.
I'm going to do that challenge right there.
And what sensors are you using? I see you have the.
How many sensors are you using?
Yeah, it's good.
0.
0 sensors on that one?
Yes.
On your main one? Okay.
Are you using 2 robots or 1 robot in the final competition?
We're using just one.
Okay, and that one doesn't have sensors.
Nope.
Okay.
How many attachments do you have?
There's this 1, 2, 3, 4, and
Thing.
45.
And then also the motor.
Yeah, yes, so 5.
Okay.
So some of you're using rotation sometimes and degrees. And do you find one works better than the other, or?
I prefer degrees partially because I feel it's more precise, but Mason likes to use rotations because he feels like it's more accurate.
Okay.
But a problem that we found with treads is that it drifts a lot, and it's not like normal wheels where you can just up, like if it drifts this way, we can't just up the speed on this because that's not how it works. We would have to just keep trying and figure out a way to help with the drifting.
Do you have the same number of treads on both?
The same
Yes.
the same amount of pieces, but then we doubled the amount of those rubber pieces.
And we made a spacer so that we can easily, so like with this, we can easily, so we would just put this on, and it would be extremely easy to put it in position because we would just have to pick it up, place it, and then run the program. So that we don't have to take time.
Do you have one mission to run that you can run? That you want to run, or?
Do you want to run like the critter crossing?
Sure.
This was our first mission we programmed was Creator Classroom.
Okay. What kind of design process did you guys use when did you pick a mission and then try to build a robot to that, or did you have the robot and went for a mission?
We kind of chose the mission and then went off of that to build parts onto that and complete it.
Okay.
Oh, that program isn't on here. Remember?
Oh. Yes.
So
What was the most successful mission that you have had?
we do have the program for that.
It's the,
Solar panel?
I think that's M1, the space travel.
How many programs do y'all have total?
5.
Do you have any loops or any reuse of the code?
I do not think so.
I didn't see any of these up here.
Yeah.
No, I haven't seen.
And because of the drift, for this one, a way so that we didn't have to mess with the coding at all, we just angled it so that it would ride the wall.
Okay, go ahead.
And we also learned that if it gets stuck like that easily, we can
Mason,
push the wheels in.
It's sometimes also it just
I know.
doesn't work all the way, in which case we would send it
But
twice.
that is
You
sometimes the
you
case.
retry, right? Okay.
So you're running against the wall, you run the treads on the wall?
There you go. Okay. Very nice. Very nice. Okay. Let's see. Can we go ahead and I think that kind of brings us to the end. Let me go ahead and take a picture of this.
I'm Grace, and I'm an 8.
I'm Daenerys, I'm an 8. I'm Houston, and I'm 8.
I'm Mason, I'm in 6th.
I'm Gabriel, I'm in 6th.
So this is a little bit about us, where our team consists of like different varieties of age, like ethnicity and religion, and like a lot of us didn't really have robotic experience, so we just decided to come in all at once, and we just tried our best to work. And now we're here at State, so pretty happy about that.
So our problem to our project is that astronauts are not able to communicate to their friends and family on Earth, and that might be a problem because they don't know what's going on, and they might start worrying, and they don't.
What she's trying to say is that a lot of people can't communicate with their families, and it's a long distance. So we wanted to create something to work to make it.
Yeah, because astronauts need to communicate with their friends and families because they should have a meeting to go into astronaut space with their friends and families.
Our solution was actually these satellites that are on a desk, and we needed to make them very powerful. We needed to make them at least 401 million kilometers, which is the distance between us and Mars when they are farthest apart. So, and we needed the dish back on Earth so it can receive the data and transmit it to the families, to the astronauts' family.
Our research
was that we researched many things like the first LEGO League, satellites, communication, and space, like what William said about the distance between Earth and Mars that's farthest was 400 million kilometers, and stuff like the average cost of a normal satellite launch. And, yeah.
So we had help from pros like Amber Phillips, who is a business systems consultant who helped us prepare for interviews, and then Jackie Anthony Lopez, who is a technical analysis, helped us also with interviews, and Samantha Scarborough tried to helped us with designing it. She was a old first LEGO League team member, and then we had Dr. Carol, who is a computer science teacher at CSU. He helped us with pretty much
a lot of
actually.
things. And he's with us right now.
He just kind of guided us through what we were doing and made sure that we were like on the right track for what we were doing.
And emotional help.
Yeah.
Mostly emotional support.
He helped us with any questions, anything that we needed help with, and yeah.
And he's one of our coaches.
We also had Thomas Schertz, who is I think he's an engineer at NASA, and we discussed our idea with him and proposed it to him.
Our first satellite was very similar, looked like a children's toy. Second, third was more advanced and was used to represent the long-distance communication between Earth and Mars.
Houston?
Our innovation is when we first started for LEGO Robotics, we didn't have a lot of team members. We didn't have a lot of experience with the first LEGO League. But over time, being at those last competitions, the regionals, the super regionals, we recruited more team members to join in on the LEGO Robotics team, so we can learn more about robotics and Legos, and that we can improve our main projects, our core values, and everything we have.
Yeah, and every time we went to a competition, our confidence grew a little bit because mostly with members, you can get really nervous whenever you're going to these things right now, and so you could get you get scared. So every time we went, our confidence kind of grew, and we got more. Yeah, we communicated more.
Yeah. Oh, and that was our project, basically.
Well, thanks. Can we ask some questions?
Yes.
Okay, so tell me, I'm still a little confused as to how your solution works. Like, how long does it take for a message, if you're communicating with someone, you're talking to a family member on Earth, how long does it take to relay the message?
Well, it's supposed to go if it would actually get built and it would it's successful. It's supposed to go instantly, as if instead of usually someone has to go to NASA and try to communicate with their family, but you can't always do it. So our idea is to where you can call them on your own phone and be able to call them whenever. That's how our satellite is supposed to work. That it goes instantly, right then and there.
Kind of like Skype or FaceTime?
Yeah, and the connection is good, no static, everything's.
But all the way to the Mars, there's not a delay?
No, that's how it's supposed to, it works to where it goes all the way.
Like,
We would probably need another like satellite to repeat the message.
Yeah, it would go from Mars to a part of like like an area, and then all the way to Earth. So it's not gonna go fully towards Earth. It's just gonna like kind of.
We'll go halfway to one satellite and
Go to the other one. Yeah. So.
So there would be somewhat of a delay, but it would be, it's like communicating from here to Finland, and then multiply that by like, what, 40? 40, like, but when I call my grandma and grandpa on the phone, they're currently in Finland, then it's nearly instantaneous. Like, it's no difference between calling someone right next to you. So with that kind of stuff, it's it's basically no delay.
Yeah, I've got a question, because currently satellites exist. So you guys obviously are just looking at a new application of an existing
To improve
thing.
it.
And how would y'all do that? What's the,
Say again?
how would y'all do that?
Probably like have like higher equipment and like more gizmo gadgets to like heighten the megahertz off it.
Have y'all done any research to kind of look at exactly what y'all would need to do or what needs to be done to enhance it?
Really, the solar panels on the sides that look like wings, they catch the sun and it draws its power from that. And the wings, we could just make them a lot bigger so that it could catch a lot of sunlight to turn it into power, and that power, and we would use that power to make the radio waves go a lot faster.
And also with our satellite, it could also improve communication on Earth, like from different places, like places that are not like good with communication, kind of like different places like Antarctica or stuff like that. It would also help improve communication on Earth also.
Like there are 3 kinds of satellites here. Are they different with the jobs?
Okay, so this one was our first one, but I mean they're practically the same. It's just that what we're doing is that, but this one, it was our first one. It kind of looked like a child's toy, and then what we would do is we would build that so it can like be on the Earth, so we could like when it sends the message, it can send it straight to the satellite. But the thing is that these two are stronger than this one because it would have like more gadgets and.
So why are we developing that one then?
We're trying
Okay.
to.
Okay, so we made the first one and we just continued to innovate it through time, like during the process of going through competitions and seeing like what we needed to fix and what we did wrong to that one. So we built 2 more to like innovate it.
Yeah, and right now we're just trying to show how we, like how she's saying, like we innovated. It doesn't, this one doesn't really do anything. We're just trying to show you guys how we made it from looking like this to make it look more like a nicer model. Yeah, more professional.
For this one, we added a dish so it would receive it. Instead of transmitting it to it, it will receive it.
So how did you get the satellite to look like this and look like this? Like, what are your sources to develop into that?
That's Daenerys.
Daenerys like
Our
about the
our sources are literally a picture on a computer. If we build it off of that, a picture on.
How did you get pictures on the computer?
Just Google satellite.
We really just used Google Images, used the source image, and I just built off of that.
And we kind of tweaked it to look different than most.
We wanted to make it look more like ours, but we used others as an example for us, but we added more to it.
Okay. So in terms of presentation, who have you done this presentation for?
We did it for that webcam thing. That thing?
Yeah.
I think, yeah. And we practiced it many times in front of.
We've done it against teachers, students, high professional people.
Who
and
are
that's what we're-
professional people?
Thomas Schutz, NASA engineer.
And we also did it in front of our mentors and coaches.
Yes.
So what was his thought, NASA engineer? What did he suggest, like, did he write the prototype?
I think we called him like closer to the beginning and just like bounced our idea and said, okay, what would we be looking at with this kind of a thing? And he was like, okay, it would cost like about this much, and it would take like this long to build. And then after that, we developed those and made our poster look a lot better.
Oh.
Are you ready? Is your field set? Are you sure? Oh, come on. Are you ready? Yeah. Is your field set? Yeah. Are you sure? All right, we will go on blast off. 3, 2, 1, blast off!
Oh gosh. And we've been blocked. Oh, okay. Perfect. Uh-oh.
Seconds, 1 minute, 50 seconds.
It's fine.
1 minute, 30 seconds.
Yeah, real quick. Let's wait for Thank you.
30 seconds.
What would count against them is if while picking it up and lower the gate. Okay, sorry guys. No. So let's find.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and time is up.
We done? All right. Okay, perfect.
All the way back, all the way back. It's in.
Okay, thank God.
Our wheel has to be inside.
Okay. Get it outside the base.
Don't keep doing it. McKay, don't. He needs to try something else. Okay. I mean, we're not getting bad for a first timer. Hey, we got points! Woohoo!
1 minute.
Oh gosh. See how quick they are? They're like reaching in there and putting things together quickly. We need to get one of those tray things. Yes, okay. We did way better than the other two.
We still have like
30 seconds.
Come on, McKay, you can do it.
Easy, McKay. Yeah. Are you gonna try Crater Crossing? I think they are right now. Yeah.
10 seconds.
Yes. Yes.
No!
5 seconds.
He was doing perfectly.
Time.
Hey, at least we showed it's all terrain, you know?
job, Rangers.
Probably.
Get a picture of that. I didn't get